Okay. So, good afternoon. Thank you very much for joining this SHAIO webinar. And as always, we are going to proceed to record this session. And we are going. Okay, today, as you can imagine, we have a hybrid format webinar. We are here in person at the Faculty of Economics at the University of Zaragoza and online. And we are very pleased to have and to introduce our guest speaker today, Professor Esteban Fernández. Let me just some words. As you probably know, Esteban is full professor of economics at the Department of Applied Economics in the University of Oviedo and principal researchers of the Group Regional Economic Analysis Laboratory, REGIOLAB. He has been president of the SHAIO, the Sociedad Esteban Fernández Vázquez, expert in econometrics applied to regional and urban analysis, econometric modeling, entropy measures, input-output analysis, and regional economics. Esteban has made highly relevant contribution and methodological advance in various fields, especially in estimation strategies in presence of uncertainty, and published in renowned journals as Economic System Research and Energy Policy Journals of Regional Science, Regional Studies, Spatial Economic Analysis, and so on. He has also participated and led several international and national research projects in the fields of regional economics, territorial inequalities, and spatial equity. And Esteban is also the chair of the scientific committee of the 10th SHAIO Conference on Input Analysis to be held in Gijón this September. So thank you very much for being here. Thank you very much for your willingness to host this important conference for us 20 years after the beginning of the 20 years later we are going to come again to Oviedo and to Asturias. And today, our speaker, Esteban, will represent a recent and interesting research entitled No More Gambling, Estimating Non-Survey Regional Input-Output Tables by Averaging Location Quotients. But I think that now, or at the end, now, the presentation. At the end, okay. And after the presentation, we are going to give him 5 minutes to present the most important things that we have to remember regarding the SHAIO conference. So, Esteban, thank you very much for accepting our invitation and the very first.
Okay. I don't know if you, well, I assume that you can hear me, but I don't know the people on at the other end. If so, please react somehow, and also we'll check if you can hear me well from here. Okay. So, well, let me start by thanking the University of Zaragoza and the Faculty of Economics and Rosa and her group for inviting me. This started with a small-scale seminar, but ended up being streamed as part of SHAIO activity as a webinar. Hopefully you are hearing me now. No, it's great because this was something that we started during the lockdowns in the pandemic, but this has been happening, and I think it's a good way of keeping the association alive with some activity and everything. And the paper I'm going to present is a joint paper with Professor Jeffrey Higgins. It is about input-output analysis, obviously, but there are not, I think I have one input-output matrix on my slides. And it's about regional analysis. Sophia is doing something.
Yeah.
I'm not responsible of what's happening now on your screens.
1 minute, yes, 1 minute. Because apparently it's not.
It's not working? It's not full screen?
No.
Aparentemente esta pantalla ya está mejor.
Okay.
No, yes.
It is full screen now?
Yes, it is.
Okay. Hopefully it is. Okay. Well, this paper is about estimating regional input-output tables. And please be aware that with regional I mean something that is produced at small scale. Okay, it's not, let's say, country scale. Okay, it means something that it is produced for a small economy, because this is part of my introduction. When we try to do some impact analysis, it is very usually we would like to have an input-output database that it is not available. So imagine that you want to conduct an impact study for the city of Zaragoza, and you don't have an input table for the city itself. If you're lucky, you have an input-output table for the region of Aragón. Okay, or if you want to conduct some regional analysis for some particular region of Spain, not all the Spanish regions they have produced. They have a statistical office that have produced for you input-output table. So you have to estimate them. Okay, and this is a kind of old problem. If you are lucky, if you are extremely lucky and you have very good information about aggregates with regional and industry details, you can apply some type of RAS adjustment. Okay, so basically you try to balance a matrix because you know the margins of this matrix. Departing from some prior, you try to do that. But this is not the typical case. The typical case is that you just have a little piece of information, which I will try to explain later, what is the typical case. But you try to exploit this information, which comes in the form of some location quotient coefficient. And this is coming, this type of literature is coming already from the 60s. So basically, what you are doing is combining this national, let's say, input-output table with your quotient. And by combination of both pieces of information, you produce your regional input-output table at the desired spatial scale. And as I'm mentioning, this is a strategy that has been going on already from the 60s, but more recently there have been some kind of proposals, mainly coming from Professor Fleck, which he suggested just to, using the same strategy to rely on a, let's say, more sophisticated strategy that depends on some parameter that somehow reflects these ideas of agglomeration economies or regional sizes. Okay, so basically, what you have is something like that. So you have see, this works well. Of course, you cannot see this, but I'm pointing at my side. So you have a national technical coefficient, but you would like to have a regional technical coefficient that has been marked with a, with a superscript R. Okay, and you have some type of location coefficient based on some observable data. This is the typical information that you have. Because if you're lucky, you have information with some industry detail, either about employment or about value add. Okay, and you try to take advantage of this information by producing some location coefficient. So your national technical coefficient times the corresponding location coefficient produces your estimate of the regional element of your. Of course, this quotient can be larger than one. Typically, what you do on this case is that you stick to the national coefficient, so you don't modify it. And there are different alternatives. The first two ones that I'm mentioning there, in say, in kind of normal form, the simple or location quotient SLQ, has this formula that you can see there. So basically, it's the typical location quotient that it is applied in regional analysis. But there are modifications of that. So the next modification, it is not a comprehensive list. Okay, there are more proposals apart from that. It is called the cross-industry LQ, which takes into account the different sizes of the industry selling and the industry buying. By doing that, it's like putting a simple LQ in relative terms. And the proposals that I was just mentioning, coming from Fleck, the so-called FLQ, It is based on the previous coefficients that are smooth by being multiplied by a lambda, let's say, adjustment factor that somehow makes this adjustment, let's say, smoother. And actually, there are two versions of that. The original FLQ that has this form that you have there. It depends if you are trying to estimate the technical coefficients that you have in the main diagonal geometrics or not. And you have the so-called augmented FLQ or AFLQ that has this form that you can read there. Okay? Maybe you are wondering what are these lambda factors. These lambda factors has this form that you, this expression that you have there. This really complex log type function. Okay, that at the end depends on this lambda, delta parameter, which is bounded between 0 and 1. So if you have a 0 value, basically you will stick to the SLQ. So there is no smoothing there. Okay. The story there is that depending on the value of this delta, you are producing different estimates. Okay. And well, there are subsequent modifications of that, even more sophisticated, even more complex forms of that, the so-called FLQ plus, which try to do, well, it's basically the same strategy, but with some minor, in my opinion, changes. But the thing is that this type of strategy depends a lot on the value of delta. And there has been some prior studies that show that this works well, actually works better than other of the alternative approaches under the right values for delta. So if you're able to pick an optimal value for delta, okay, you are doing really well in estimating these regional input-output values, okay? And this conclusion is mainly based on numerical simulation. So there have been some authors that say, okay, let's do some Monte Carlo simulation, some numerical experiments, and let's try to identify which are the values of this delta parameter that work really well. Okay? So this is the context, this is the background. And there are more studies than this one, but I'm taking this as reference. This is a relatively old paper published in Economic System Research in 2008 by two Italian professors, Andrea Bonfiglio and Francesco Celli. Okay, they are basically investigating that. So, okay, this is the context. So, what are under which circumstances, under which values of this delta parameter we can rely on our estimations? Okay, and I will give you more details later on that. But basically, what they do is they generate artificial, experimental, multi-regional input-output systems with 20 regions. 20 industries, okay? They generate these values, let's say, numerically, then they aggregate, and they are trying to produce these matrices of regional technical coefficients, departing from the national aggregates times the FLQ or the AFLQ. Remember, flag location quotient or augmented flag location quotient. Under different values of delta. So they start, okay, what if delta is 0.1? What if delta is 0.2? What if so until 0.9? And they draw 1,000 simulation flows each time. Okay, and then they, given that they have generated the regional matrices, but they are acting as they didn't know that they can compare the real values that they are generating with the estimates that they are producing by following this strategy. So you can calculate a measure of error. In particular, they are paying attention not only to that, but mainly to the so-called mean absolute percentage error. So you take the absolute value in relative terms times 100. Okay, so you have a measure of error as a percentage. And well, there is a lot of stuff in the paper that you can check. But on my final point on this slide, you have a good summary of what you have. So they say, okay, this strategy of the FLQ and AFLQ they work really well if the values of delta are in the range of 0.3, 0.4. Okay? In such a case, they work really well on average. Actually, they are let's say, they are more detailed than that. They say the augmented strategy did better if if delta is like 0.3 or less. But if you make delta 0.4 or more, then let's say simple FLQ does better. Okay, but this is kind of tricky because this is just on average. But in terms of the risk, the variability of the error, so the risk of producing big errors, it is better just to have high, or at least higher values of delta. So if you are like 0.8, 0.9, in terms of the variability of the error, you are, let's say, safer. So, okay, great. So at the end of the day, you want to have input output table for the city of Zaragoza, and you want to follow this strategy. Which delta are you taking? Okay. And some authors say, yeah, okay, this is an issue. We have a problem. And there is a paper published in Regional Studies in 2012 by these two Finnish guys. Yeah, I think I'm not able to pronounce them properly. Then, well, these two guys there. So basically, they say, well, it is kind of being lucky, just like a game. Okay, so you make a bet, you take your strategy, you take your delta, and you see what happens. So the question is this really? I mean, if you are following this path, are you like, taking a bet? And no, actually, it seems so. Okay, and I'm trying to illustrate this with a recent paper published in Papers in Renal Science in 2021. Yeah. By three Spanish colleagues, on which they try to investigate this. I'm going to give you more details later. But basically, they're saying, okay, if we try to apply the FLQ for cases on which we already know the regional input-output table, okay? But we follow this strategy, so we depart from the initial one, and we apply this, we compare our estimates with the true regional input-output table. What is the best delta that we can produce? And they investigate two cases. The case of South Korean regions, the 17 South Korean regions in 2015, okay, and like 13 Spanish regions across several years, for which we have survey-based regional input-output tables, okay? And they are trying to investigate what is the optimal value for delta on each case. And if you have a look at this table, so for example, in the case of Korea, you are finding values of delta as low as 0.18 and as high as 0.50 something, or 0.6 in the last case. Okay. So this means that for region number 2, Seoul, on this table, the best value of delta is like this 0.18, but for the last region, on the last row on my table there, it is as high as 0.6. Okay, and if you just shrink these two values, you are not getting very good results. Well, if you focus on the case of Spain, I think it's even worse. Because for the case, let me check this, for the case of the Balearic Island in 2004, the optimal value that you can use is less than 0.1, but for Aragon is more than 0.6. Okay, so what is the conclusion here? Again, you want to produce a regional input-output table or a local input-output table, and you want to follow this. What value delta are you taking? It looks like a gamble at the end of the day. Okay, but Fleck friends were not very happy with that, and they produced this kind of reply paper in 2016, Regional Studies, and they said, no, this is not a gamble. Okay, you can be kind of systematic and have a method to pick the optimal value. Okay, remember that you don't know the true value of the regional input-output table. Okay, you are able to produce tables like this, results like this, in cases on which you actually see it, and you try to get some type of pattern, These other guys were saying, well, I mean, it's not good news because you are seeing this high variability there. But this other paper says, no, this is not a gamble. You can do this on a systematic way and try to, how should I put this? Try to have a method to identify which is the best delta that you can apply in advance. Okay? And well, they try to do some econometrics here. Okay? So they, for example, start from the system of the 17 Korean regions. Okay? And they say, okay, so we are trying to relate this, you see this, optimal deltas that you have there on this table with some regional characteristics. Okay? And we estimate equations like that one that you can see on this slide, in order to predict that. Because if you're able to get estimates of these parameters alpha, beta, and gamma, and you have the necessary information of the regressors, you can produce kind of predictions for the delta. Okay? Actually, it's a bit more complicated than that because they don't have one single equation, but they estimate one equation for each region. So basically, they take out a region and they estimate the equation with the remaining 16 regions. Okay, but just keep it simple and let's assume that we are trying to estimate an equation in order to produce the best, the optimal values for that. The regressors that they are using for that is R is the regional size, is the percentage of the output of the region in the total economy. P is some type of information in propensity, regional propensity to import. And F is the average gross output of each region imported from abroad. And perhaps you are starting to see some problems there. Okay? These results that you have there on the table are based on that some results that you can see on this paper that I was mentioning before. Okay, so you have the intercept, the alpha, the beta, and the gamma estimates for each one of the 17 algorithms, and you can see that there is pretty much variability there in alpha and beta and gamma. Okay, so because if we have exactly the same values, you can say, okay, if I have the information of the regressors, I can rely on these parameters and produce prediction for my delta. But the thing is even worse if you try to do the same with the proposal by these Spanish authors. Okay, because first of all, they changed the specification of the equation. Say, well, the previous equation is great, but we have a better proposal. And now it is not a log form, first of all. And now it is based on this I rho, which is the share of imports from the rest of the world for one particular region. And IRFT, which is the interregional weight of rail freight transport flow from our regions. Okay, and they do the same. And they take exactly the same data set for the 17 Korean regions, and they try to estimate this following the same strategy. And you can see there the estimates for alpha and the estimates for beta. Okay, and you can see that, well, alpha, well, maybe things are a bit better now because alpha is in the neighborhood of 0.15, 0.16, something like that. Beta, it is around 1. Say, okay, maybe we have something here, and maybe we can rely on that in order to produce the best possible data. But you go to the Spanish regions, and you try to do the same, and it is kind of a mess, because by doing the same, now, look at this, alpha was like 0.15 for South Korea, for Spain is like 1 point something. And beta, well, it was like 1, but now here is like 0.7. So, okay, this is not good news. I mean, it is really, it was a nice attempt to, let's say, reduce the arbitrariness that we have there when trying to set a delta value. But the problem is that we have a lot of issues here. So the first obvious problem is, well, which is the right equation, what is the right specification? Because there is no theory at all, or almost no theory at all. Okay, so this is the first issue that we have there. So the functional form, the regressors that you're considering, and all this stuff. Second, the regressors, you have to be very lucky to have access to this information. I mean, with a numerical experiment, of course you have it, but in real life, it's really difficult for just having information on output for industries and regions. If you're lucky, you have value added, but in many cases, you don't have information on output. Not to mention the other regressors that they are considering there. Okay. More things. The econometrics there, it is kind of, I mean, they are based on just a few data points. For the case of Spain, they try to estimate an equation with 12 data points and 2 parameters, 3 parameters. This is not great. Okay. And as you can see, there is a large variability in the results. So it is really difficult just to get some kind of pattern there. Just to have a kind of universal rule of thumb saying, okay, this is the way of setting a value of data that I can use for my problems. Okay? Okay, so we have a problem here. And what is the problem or what is the solution to this problem that we are trying to investigate? Well, let's keep things simple. Why gamble if you can average? Because this is a problem that we have in other fields of economic analysis, in particular in the area of forecasting, of economic forecasting. Okay, so if if you're trying to forecast a future value of economic variable, you can of course have your model and your regressors and try to derive some mechanism there just to predict this value. But there is a consistent result in this type of literature that it is called the forecast combination puzzle. Okay, and actually this has 2 parts. The first part is that it is typically better to average several forecasts rather than relying on one single forecast. On average, you're going to do better if you average rather than if you rely on one single forecast. Okay, this is the one part of this puzzle. The other part, it is more intriguing because it says, and the best way of combining potential forecasts, it is just taking the simple rule. Even if you know that some models are better than others, even if you try to do some type of complex Bayesian combination of predictions, the best possible strategy on average is just take the simple rule. Okay? And this has been there in this type of literature like forever. Okay, and say, okay, maybe what we have here is basically the same. We have several potential, several feasible results. Okay, we have no prior reason to think that one is better than other. So let's take everything and let's average this. Okay, and let's check if it is at the end of the day better than coming up with a fancy econometric regression and just say do this. Okay, and this is what we are trying to do in this paper. Okay, and actually we try to investigate this by following basically the same strategy that the 2 Italians that I mentioned before. Okay, actually we are relying on the same framework for evaluating our proposal by means of a numerical experiment. So we have the same framework in the sense that we have R regions. We're trying to make this more general, and K in our case is always 20 industries, and we are generating the values on our numerical simulation. So generally, the values of the inter-industry, inter-regions matrix of flows, of trade flows, the C's that you have there, are generated as a uniform, excuse me, between 0 and 100, but then we adjust this. The first adjustment that looks like complex, but it is not that complex. It is like saying, okay, but the volume of the trades that you have for within the region are bigger than I said within regions are bigger than between regions, right? So we are saying, yeah, okay. So this first line is our baseline, but then we are modifying this if regions R and S are different, so it's between regions. multiplying this time factor that uniformly distributes between 0 and 0.05. And we also introduce another adjustment, which is a kind of integer, 0, 1, just taking into account that in real life, you have a lot of zeros in multi-regional input-output tables. Okay, so you have cases for which there is no trade at all. Okay. We also are adjusting our initial generated matrix by inflating the cases on which you have intra-industry flows. Okay, and then we basically sum up things in order to produce a vector with the intermediate consumption, and we are generating also value added. Okay, as some adjustment from the total of intermediate consumption. So we are basically saying the value added for some industry and region can range between 50% of the intermediate consumption up to 2 times the value of the values of the intermediate consumption. And we are producing the total of imports. So at the end of the day, we have this matrix C, the value added, and the output. Okay. So with the C's and the C matrices and the outputs, we can produce technical coefficients, the matrices of technical coefficients. So this super matrix A is a matrix composed by matrices. So in the main diagonal, you have the regional, single regional input-output tables, and the off diagonal elements, you have all the inter-regional coefficients. Okay. So ARR represents the technical coefficient matrix for region R. And we, as Bonfilio initially did, we are just focusing on the estimation of this main diagonal. Okay. So given that we have generated also value addeds, we can generate LQs. Okay, based on these value addeds. So we can we assume that we have access to this information of the value added. So at the end of the day, we have this kind of super matrix that we aggregate in order to produce a national aggregate. Okay, this allows us to produce a national coefficient. We have also the value added to produce the LQs. Okay, and we are investigating how the FLQ and how the augmented FLQ works under different values of delta, of this parameter delta. Okay, and we start exactly with the same framework as Bonfilio and Michele. So the details of the numerical simulation that I just gave are basically the same as they do. Okay, and we are relying on these MAPE figures. Remember that this is a measure of relative percentile absolute difference between the real values that we have and our predictions. Our predictions are the P's that we have there. And these predictions are produced by following these two strategies, FLQ, AFLQ, given values to delta like 0.1, 0.2, 0.3. So for each case, we have 1,000 times the simulated matrix. Okay, and what we do is just to represent the results of the FLQ in what? In green. The augmented FLQ in pink, our proposal in blue, not a good choice, maybe for Jeff, but not for me. In blue, so we have the mean of all the potential results. Okay, please be aware that it's not averaging the deltas, it is averaging the estimates. Okay, we average this, and what you have on this kind of histogram there, it is the distribution of our errors. Okay? And you can see that the risk of making large errors with the blue figures is really small. Okay, so these values, these values around here, so are really big errors, correspond to the red, pink and green results, and even on this area, you almost have no blues. Okay. Another way of seeing that, it is just counting the times on which each method is the best or the worst. Okay? And for example, on the bars that you have at the left, you have the count of times on which the augmented, again, in kind of the AFLQ is the best, or the FLQ in green, and in blue is our mean. Sorry, the first one that at the left is the worst. Okay, and you can see that it is just a small fraction of cases on which averaging is worse than the other two strategies. The other part of the picture is what you have at the right panel. Okay, so it's the best. So you can see that it is only in a marginal case when following one of these specific strategies that's better than just average. And you can say, yeah, okay, nice, but you are kind of trying to, well, you're doing a tricky thing here, because on this summary of the results, you are considering all the values of the deltas, okay? And this other Italian guy said, well, this works well if delta goes like 0.3, 0.4, and you are putting all these kind of values of deltas that you are never using, okay? I would say, well, yeah, well, this is a possibility. So what if, instead of averaging all the potential range of values for the deltas, we are averaging just the optimals, okay? So we are taking out all the extreme cases, and we are just focusing on these kind of middle values, 0.3, 0.4, 0.5, okay? So we are just taking out all this stuff, basically, okay? And we are left with something like this. Okay, even so, averaging seems safer. Okay, if you have a look at the distribution of the errors there. Of course, well, some part of the really large errors that you have there are gone, but still looks better just to average than doing that. Please be aware that I'm averaging everything. Even these worst values that I'm not showing for delta, in this case, they are considered for my mean of results here. And even so, I do better than that. Okay, and I show you these graphs. Well, of course, the scale, of course, changes, but the pattern is still there. Okay, and you can tell me, yeah, but still being tricky because you are considering all the values of deltas for your average. What if you just average the values of delta that you are considering there? I say, okay, fine, you have a point. So I'm doing that. And nothing changes really. Okay, these are my new results. And if I show you the previous graphs, still, well, of course, there is some change of the scale. It seems to be better just to average everything. But still, you are safer just by averaging on average. It is better to average on average rather than relying on one particular value for your deltas. Okay. We did, among just almost reason, we did some kind of sensitivity analysis there, because you say, okay, to what point this depends on the number of regions that you are considering. Maybe if you are considering a smaller number of regions, things change, and actually it is not the case. Because we have tried with the same experiment, but only with 10 regions. This is what we have. Okay? So, well, it seems to be the same. But what if instead of 20 regions you have more? So let's say 50. It's the same story. Well, it's actually clearer this type of reason. Okay. So, and this is my final slide. Some very, very preliminary conclusions. So, if you are trying to produce a regional input table with this lack of ability of data that prevents just to apply some type of adjustment based on well, some adjustment to the totals, RAS type thing. Okay, if it is maybe you are only option to rely on this LQs thing, but if you're trying to do that, maybe you should consider this alternative rather than rely on these other guys on the literature that apply some particular value for delta. So it is kind of safer way to produce your estimates. Okay. Of course, it's still work in progress. We are exploring all of this. So first of all, we are just paying attention to this absolute error, but this is not the only way of capturing divergences between your prediction and true values. This is fair. There are other metrics for that, and we are exploring this. I can tell you that at the end of the day, nothing changes. Okay, the scale changes, but the results not. And something that we are exploring, because if you remember, we are just paying attention to this. So what happens with the other parts of this system? Okay, and typically what you are doing in order to produce estimates for these off-diagonal matrices is just to rely on some type of gravity mechanism, on which the problem is that we have essentially the same type of problem, because you need to set some parameters for the masses in your gravity and the distance. Okay, and we are trying to explore the possibility of following the same type of strategy for this type of analysis, just saying, okay, let's try with different values for the, in this case it's more complex because we have more parameters, and because we have more regressors there, and just by averaging the results and see what happens. And I think this is the last slide. Hopefully this has been interesting for you. Thank you. I don't want to touch anything because yeah, maybe we can go here. I'm quit sharing. Okay. Yeah.
You can moderate yourself.
Okay.
Yes.
You sure?
Okay. Because if I go, okay.
I don't know if it's better if we start taking questions from here or from the audience in the.
Any question? Okay, so let's go to the chat. To the okay, we have time for questions now.
Yes.
Press your hand, so.
Maybe Jorge, or I don't know if Jorge is asking something. Or...
No. I didn't ask anything. I think Bart is going to ask something.
Wow, you're mute. Okay, you're not mute.
Yeah, well, I hope you can hear me, but I can't hear Rosa, so it was unclear to me whether you would first take questions from the floor or first from the online.
No, you can.
Go ahead.
Go ahead.
Yeah. So thanks for the presentation, Esteban. Of course, it is very important how to estimate these regional tables if data is scarce. So it's clear, at least based on what you showed, and I would not be surprised if that would be confirmed by additional investigations, that your approach yields better estimates, at least on average, than those that were proposed before. But still, if you look at these mean average percentage errors, they are in the range of 50% or something like that. So my question is whether you think that any analysis based on these location quotients with a uniform delta over industries or products is a good way to proceed. Aren't you more or less suggesting that the bounds of what can be achieved by this approach have been reached, and you can move them a little bit into the right direction, but not too much? So shouldn't we focus more on industry-specific approaches, and then, for example, also taking into account that some regions are islands, some regions are far from the interior of a country, and I don't see why a uniform delta should solve these types of heterogeneities across regions and industries. So do you have some ideas about this?
To be honest, I think I don't. But what you are suggesting, I'm not sure if I'm fully understanding what you are suggesting, but I think it is like saying, well, it doesn't make full sense just to take into account all these range of possibilities, and you can use some type of additional information to say that some results are more plausible than others, taking into consideration particular characteristics of the economies, the regional economies that you are investigating. If this is the case, yeah, I mean, you have a point there. I mean, you can depart, and this, we didn't investigate that, so we just started with this very simple exercise. But in the other field of literature that I was mentioning, which is forecasting, there is some strand that basically departs, in principle, you depart from a simple mean, but you, this is your prior, and you try to put additional information there, if available, and just to, let's say, change the initial uniform weights. And this is perfectly possible, and it could work well. But if your question is if, as a kind of strategy, I would recommend using this type of strategy, just because you're completely right. Sometimes the errors are very, very large, in the neighborhood of 50% or more. The question is that they are bad, but there is nothing better than this, unfortunately for us. In the sense that there are many people following this strategy, just because it's the only option that they have.
More questions? I have one. I was wondering about the term, the reference, the real economy, to which to be more close is better, because at the end, when you present the estimation of the input-output tables in Spain, the regional input-output tables, for me the problem is that in the case, for instance, of Aragon, but La Rioja, etc. Yes, for instance. Most of them are estimated tables.
Oh, yeah.
Real tables. And I was wondering to what extent the estimation of the delta is reproducing a behavior that is behind the estimation of the real tables.
This is one of the problems. And it is not only for Spain, but also for the South Korean regions. Okay. Yeah, I mean, this is so, you are relying on thin air, this type of research. In my opinion, it is almost impossible just to derive some kind of pattern in order to investigate, in order to grasp the real delta values. Yeah, I don't rely very much on these results. I mean, I agree with you. No, I was just using that just to illustrate that this is so problematic that maybe another strategy is better.
Yeah, but also in your strategy, I mean, the delta is based on the share.
No.
No, it's
just say, okay, which are potential values for delta?
Yes.
So let's say 0.1, 0.2, and I take these 10 possible values, I produce 10 estimates, and I just average. Well, I do this like 20,000 times each, and I have something like that.
It's about news for the techniques.
Well, it's not good news for that.
There are two hands raised, Rosa.
Oh, sorry, I'm not seeing the screen.
Jeffrey, I think, and I don't know, the first is Oscar?
Oscar Lemmers too. Yeah.
Okay, yes. Please.
Thank you, Esteban, for this wonderful presentation. Very, very useful. In the Netherlands, we try to develop regional input-output tables, and we run into the same problems as everybody. I would like to refer to the question of Bart. You can still hear me properly because I hear a lot of echo.
Yeah, I can hear you more or less. Yeah, just go on. I think I can understand what you're saying. Maybe there is another microphone open.
Well, Spain, Netherlands is a long distance. I was thinking the industries. In the Netherlands, we are in the lucky situation that we can do something properly for goods producing industries because we have the transport flows. But services are really, really difficult. And I might have missed something, but I think you treat all the industries the same. It is, I can put the manufacturing, I can put it separately, I can treat them in the way I want to. But even in services, there are the not so tradable industries, getting a haircut, which is very local, or going to a music concert, which could be very non-regional. Do you have any suggestions if that can be used somehow to improve things? And I mean, I also agree with you that you say, okay, it's maybe not perfect, but it is the best we have. It is an improvement to doing everything proportionally. So any word of advice would be much appreciated. Thank you.
No, thank you, Oscar, for your comments and your question. Yeah, I think my answer is basically the same. So if you have some additional information that can be useful in order to improve your estimates, I think this type of strategy can incorporate this type of. I mean, your initial guess about your solution can include this type of additional information. Of course, we didn't do it on this presentation because we wanted just to have a very simple case. So we don't have an empirical illustration, first of all. It is just, so we just want to have something simple to present. Okay, but you are completely right. In the sense that, of course, if some additional information in terms of, well, what you were mentioning is available, this can be included. I think, yes.
Okay, thank you, Rosa. Thank you, Esteban, and greetings from even farther away than the Netherlands, the US. I'd like to just add a few things to the discussion, Esteban. First, I think since we last talked, I have discovered from colleagues in Korea that the tables on which Flegg had based his empirical estimates were non-survey. So we've got an endogeneity problem here. We've got estimates of estimates, and that's something that I think that we should be very reflective. There were some additional data that they had, like the paper you referred to with the trade data, but most of it was a non-survey estimate. So that's a separate issue that I think needs to be addressed, and we can basically just put that as a footnote. But I think it's very important that for young scholars to look at the paternity of the data that they're using and not just assume that because it is there, it's appeared in a journal, that it is without problems. And I think that's an issue. Second one is that I think if you're going to claim that there's a universal law, which Flegg has been trying to do, I contrast that with the work on the wage curve, where you've got hundreds and hundreds and hundreds of empirically based estimates at the national level, at the regional level, at the metropolitan level, and they all seem to converge about minus 0.1. I think on that basis, you can say that this works. And I think it's a little bit presumptuous for a scholar to claim that on the basis of using data for one country, that we've got some sort of universal law. Thirdly, I worry very much about the MAPE statistic because it doesn't tell us very much about the analytical importance of coefficients. So you could have a large error with a very small, insignificant coefficients, but a very small error with a very large analytically important. And this applies not just to Flegg's work, but I think to most non-survey estimation. And then two other quick comments. most time when people are estimating a model, they don't have access to the multi-regional version. But Jeffrey Round's approach to do this in a two-region, the region and the rest of the country, at least your estimate has some degree of balance with it. And I think that that's important. And what we don't know from Flegg's work is the degree to which, if we added up all of the regional estimates, to what degree would they be consistent with the national table. And my final comment is, I think the idea of delta would make more sense if we dealt with a model in which households were endogenous, because then the volume of consumption would tell us a great deal about the availability of what Oscar was very concerned about service activity, and in terms of things like retail activity, access to banking, access to legal services, business services, and so on and so forth. But even then, I think that is just a minor correction, and I think what you presented, I'm convinced. So I think it's just basically a way of reducing the uncertainty. But I think, as Bart pointed out, it really doesn't tell us whether you improve the accuracy, and that's a whole different issue that is not addressed in the paper. Thanks a lot.
Thank you, Jeff. I'm glad to hear that you are convinced, considering that you are my co-author. No, great. I can only agree with your remarks. I think there was a question coming from a John scholar in the audience here.
I don't know, probably it's PPC because you know my limitations with inputs outputs and these things, but I was wondering.
Maybe can you hear the question? Wait, yes? Bart can, but Jeff can. Yep.
No, we are not hearing nothing now. Maybe you have to open your microphone, Sophia, the webmaster microphone.
Yes.
Okay, now. Mute again. It's mute again. Now. Yeah. We can hear you, Fernando.
Yeah. Perfect. Now there is progress. Okay. Now it's just I was wondering if. Don't worry. Okay. Sorry, because it's a stupid question. No, I was wondering, in the forecasting of elections, when the companies try to forecast the results of the elections, it's very common to weight the forecasting. They combine different forecasting, and it's very common to weight according with the historical success of the forecasting. No? And I don't know if here is possible to apply something similar. If you know. If you are forecasting tables that you know in the past, maybe you can use this. And if not, I don't know if you can weight in these values between 0.3, 0.4 to give more relevance to this, if all the literature give more importance to these parameters. No? I don't know if this makes sense or if it's a stupid thing.
It is not. Sorry. No? It is not a stupid question. It makes full sense. And yeah, we can do that. I mean, with the numerical simulation, we can do that. I have to think about it. I mean, because typically you don't have a time series of tables. But let me say to you that in the economic literature on forecasting, even if you have models that are consistently better than others, even there, it is better just to take the simple method. So I don't know what's going to happen. I mean, you can do that, and just based on, let's say that you are estimating all the regions but one, and we are using the best values, and you give more weight to these results, we could investigate that. But if I have to bet, given that we are talking about making bets, I would say that even there, simple mean would do better. But I don't know. I mean, it makes sense what you are suggesting.
We don't hear you, Rosa.
So, okay.
Yeah, maybe. Oh, I was forgetting the other. No, Rosa is completely right, because we promised that there will be a short presentation of the SHAIO conference right after that. We just want to make sure. Yeah, we just to make sure that there is no other question coming.
No? Okay. So in that case, we can
Good.
have
Yeah.
5 or